సార్ సార్ విశ్వనాథ్ సార్
సార్ చెప్పండి సార్.
సెషన్ స్టార్ట్ చేయమన్నాను సార్. అంటే 2:10 అయిపోతే ఒక 5 minutes ఆగి స్టార్ట్ చేద్దాం సార్.
ఓకే సార్, ఓకే సార్, నేను చెప్తాను. ఐ థింక్ పల్లవి గారు ఉన్నారు ఆల్రెడీ.
అదే నేను మాట్లాడుతున్నాను, మేడం గారు రెస్పాండ్ కాలేదు. ఇంతకుముందు అంటే నా ల్యాప్టాప్ ప్రాబ్లం ఉన్నది, నేను వేరే మొబైల్ కనెక్ట్ చేశాను.
యా ఒక్క నిమిషం, నేను ఐ విల్ స్పీక్ టు పల్లవి మేడం.
ఓకే సార్. ఓకే సార్.
You are not audible for me, sir. Pratap Reddy garu, you are not audible for me. That's why I couldn't answer.
ఓకే మేడం. ఇప్పుడు వినిపిస్తుంది కదా మేడం?
వినిపిస్తుందండి.
ఓకే మ్యామ్, థ్యాంక్ యూ మ్యామ్, థ్యాంక్ యూ.
ఓకే,
ఒక 5 minutes ఆగి స్టార్ట్ చేయండి మేడం.
పల్లవి మ్యామ్ ఒక 5 minutes.
Yes sir, I'll wait. Pratap Reddy garu, shall we start?
Yeah, ma'am. Start chain, ma'am.
Okay, sir. Thank you. Good afternoon, everyone. Welcome to the 6th day of the online workshop on applications of modern softwares in drug discovery, development, and optimization, organized by AP State Skill Development Corporation in association with Vignan Pharmacy College. Today is the second day of the subtopic of the main theme, that is quality by design using design of experiments. We are using Design Expert software for explaining this concept. I would like to hand over the session to Dr. P. Srinivas Babu garu, the principal, Vignan Pharmacy College. Sir, please.
Thank you, Pallavi. So, so today, good evening, good afternoon to everyone. Today is the last session for the online webinar on the application of modern softwares in drug discovery, development, and optimization. So, yesterday we have gone through all the important topic like quality by design using design of experiments, which is a important topic which I and Dr. Pallavi both has narrated. And today, whatever the contents which was covered in the last webinar, so you can I want to review briefly about what's the thing. Last time, yesterday, I reviewed about the quality pharmaceutical product drug development is a very essential for the healthcare. So how the quality, safety, and efficacy effects. So what is QBD and the relationship with the design of experiments. This is one of the important topic which I have discussed, and all the material which we have given, and also what is design of experiments and screening designs, as well as response surface methods. So all these are all reviewed, and this is which we have discussed about the QBD is nothing but the predefined objective of which emphasize the product and process our understanding and process control to ensure the clinical efficacy and safety. So, and all these are all the recap which again I don't want to explain more this thing. So, but anyhow, just you go through it. The quality, sources of variability. So, which we have discussed about all the various variability process parameters like API variability, excipient process variability, packing variability, and other variabilities, and key elements which is especially very important for the QBD, like QTPP, this is a quality target product profile, CQA, that is critical quality attributes, and similarly the CPP, this is critical process parameter, and CMA, critical material attributes. All are very, very essential. I hope you have understood. And similarly, narrated about the quality risk management, ICHQ9. So this is also very important, and the importance of the quality risk management by giving the Ishikawa fishbone diagram with 6 M's. So, and this is apart from that, the design space and control strategy, product life cycle management. So all these are essential to design of experiments, which is a very important aspect. So which I have given the presentation on these areas. And coming to the next part is Dr. Pallavi has narrated about what is the design of experiments and what are the fundamentals of DOE. Similarly, the variables, like how the DOE and one factor at a time approach, because nowadays the DOE have a lot of applications and advantages compared to that of OFAT approach. And similarly, fundamentals of DOE also discussed, where like variables and what type of variables are there, like input variables and output variables. And similarly, the levels and effects as well as mathematical models, which is also very important. And the different types of the mathematical models like linear, 2f1, quadratic effects. So I hope all you understood. And the important factors, screening study and factors optimization, that is screening designs in this various fractorial, fractional and fractional factorial design, Taguchi design, Plackett Bowman design, and optimal screening design, as well as other screening designs. And these are all very important. And the factor optimizations will be done using a full factorial design, central composite design, box Pectin design, optimal design, and mixture designs. So all these are all, I hope it is given exclusively by the information. And if you have any specific doubts and information required, please mail to us, and please go through all the designs. It's very important. And also I hope some of the case studies which was given, like the DOE case studies, live designing, which was given for the different types of formulations, like sustained release tablets and all. So all these are all very important, and within this thing, and also very important topic, and which is required for the current industrial trends. So with this, I would like to hand over the session to the Dr. Pallavi for the next coming session on these areas, because which is very essential, the software, how it should be used, and what is the basic objectives of these DOE studies and all. So I request Dr. Pallavi to continue the session. Thank you very much.
Thank you, sir. Thank you for the insights given. You have very quickly revised all the concepts that were delivered yesterday, which we repetitively use in today's designing. All the terminology that we have discussed in the yesterday's session, we will repetitively use them in today's designing. So moving further, today's session is completely about designing of experiments. We take several case studies and we are going to design experiments. We are going to design the experiments using a very user-friendly software named Design Expert software. For this demonstration purpose, we are using a trial version of the software, version 13, which is the latest version of the Design Expert software. Let's see the objectives of today's session. So today we are going to be introduced to the Design Expert software, how the software looks like, what are the options present in it, what are the wizards, what are the different tabs that are present in the software. So we will walk through the software, we will understand what are the tabs present initially. Then after that, we will see what are the designs present in that, how we are going to build a design for your experimentation purpose. Among the number of designs that are present, how are you going to select a design for your experiment that you are supposed to do? how you are going to build that selected design, what are the factors you are going to select, how you are going to give the factors as input variables, what are the responses that you are going to analyze, how you are going to load those response parameters into the software, how are you going to evaluate the design that you have, that design given by the software, what is meant by power of the study, what is the delta versus sigma ratio, what is meant by lack of fit, what is meant by FDS, what is meant by design augmentation, when we do augmentation. Then we will also see about response analysis, how you are going to transform the design, is it required or not. Anova, that means analysis of variance, fit statistics, various diagnostics present, and various model graphs representing the impact of factors on responses. We are also going to review how numerical optimization is done, what are our goals, how we set the limits, how we will get solutions for the set goals, how we are representing the same solutions in the form of graphs. We also do graphical optimization today using various plots like overlay plots, 3D response surface plots. We will identify the design space. We also do post analysis. That means we do point prediction. That means what is the most desired solution among the given options. How we are going to confirm that the design is valid is what we are going to, in brief, the agenda of today's workshop session is all these. So now we will start the session by designing an experiment using Design Expert version 13 software. What we are going to design today is, we will see two processes, that is, one is process optimization, other one is product optimization. The basic design that you can employ using Design Expert software, that is factorial design, and response surface design, example box Benhen design. We will see these two in detail, and we will also review how a Taguchi design will be all categorical factors with all categorical factors. We'll also see a central composite design where an optimization of the process is done. Let me introduce you first to the Design Expert software. Is my screen visible?
Yeah, yes, ma'am.
Yes, sir. Thank you. So all of you can see the screen now. This is Design Expert version 13 software. This is how it looks like when you open the software. Okay. This software is designed by Statis. Yes, as the tagline says, the statistics that you do for your experiments will be very easy with this software. You can do multiple tasks with this software. Let's see the main options that are present. See, you can find 4 tabs. The earlier versions like version 12, version 11, etc. will not have this tab. This is newly added tab, that is import data. That means if you have data in your Excel file, you can just import that data. See, we have 4 options. One is new design. Second one is open design. Third one is import data, and fourth one is design wizard. When you are going for designing your experiment, you will first go for new design. If you know what design you have to take, if you have a prior knowledge what design you have to take, you can straight away go to new design. You can use open design for already existing designs. See, you can see some recent files here. You can just click on this and also open the design, or you can use Open Design tab for opening existing designs. I already told you import data is for importing some results data from Excel sheet, etc. And this design wizard is what you use when you don't know what is the design that you have to employ for your experiment. This design wizard itself will guide you, will let you choose a design which is the most suitable for your experimental conditions that you have given as input. Let's see one on one. First, we will open a new design. Observe the screen once. This screenshot we have already seen in the yesterday's presentation. If you remember, at a topic called fractionation, fractional factorial design is what we have discussed yesterday. At a topic called fractionation, we have seen this wizard. You observe some white regions, some green regions, yellow. Actually, this will be red. Think it as a red. Red is stop. What level you have to stop fractionation means at this level, for each number of factors given, you have to stop fractionation at red level. Yellow is have certain constraints, but if you don't have any other option, you can still proceed. Green is good to go, good level of fractionation that you can employ for your experiments. And the white ones are full factorial designs. See, observe the screen. By default, it has left side certain options like regular two-level factorial design, minimal run characterization, minimal run screening, multi-level categoric design, optimal design, and some other miscellaneous designs like Plackett-Berman, Taguchi, etc. You also have certain other designs like split plot design, which can be used when you have 2 to 15 factors and you have some hard to change factors. What does it mean is, it is very difficult that you can't take an option to change those factors. You must not change the factors. The inputs that you give for those factors are fixed. In that case, if this is your criteria, then you can go for a split plot regular two-level design or multi-level categoric design or optimal designs. You also have response surface designs like central composite design, Box-Benham design, optimal design, and this is a newly introduced design, definitive screen design. You also have split plot designs, 2 split plot designs in response surface methodology also. You have certain other designs like custom designs where you can see optimal designs, blank spreadsheet, some other options like import data from Excel, some user-defined characteristics, you can make some new design and name it, etc. So these are these are newly added designs in version 13, the legacy designs, regular resolution, 3-level factorial, hybrid, pentagonal, hexagonal, etc. So if you observe, by default, you will be selected with this regular 2-level design. Observe this one. Let's take one example. If you want to do a 2-square factorial design, you just have to click on this 2-square factorial design. What does this 2 square indicate? Yesterday we have reviewed that. Let's take 2 cube, okay? It will be easy to differentiate the numbers. If it is 2 cube, what does the 2 represent? 2 represents levels, 3 represents factors, number of factors, right? So if it is, for example, you have an experiment where you have 3 factors which you want to analyze it, each at 2 levels. Then you will click this design. You can observe at the bottom and next button. See how the window is showing. It is showing what are your 3 factors. It is asking your inputs. So let's name my 3 factors for now, as we will see in detail this 2-level factorial design. I'm just introducing with the interface, okay? So see, my 3 factors, A, B, and C are my 3 factors. and what are the units in which you are going to measure these three factors. That means if it is time, you can enter here as minutes. If it is temperature, you can enter as degrees centigrade. If it is some percentage representation, you can enter units as percentage like that. And observe here, since our design is a 2 cube factorial design, I told you that 2 represents levels, low level and high level, right? So now for each factor, you have to define what are the levels for that factor. Imagine that you have 3 factors. For example, let's consider temperature as one factor. So for temperature in your experiment, what can be the minimum temperature that you have to employ and what is the maximum temperature that you can employ? How will you decide this? Based on your output? Okay, you have to do some preliminary experiments to fix the levels. Okay, you just can't put some value here, because any error in this area will make your whole experiment go wrong. So you must be very cautious at this step. You have to fix right levels. Okay, your low level and high level must be very much accurate to the factors that you have considered. Then you can click next. If you observe the next screen that is being displayed, that is responses. We have 2 types of variables. If you remember, input variables, output variables. The factors are input variables. Responses are output variables. See, you have to enter the name of your response. For example, yield is my response. Drug release is my response. Assay is my response, like that. And if you have more than one responses, you can use this arrow mark to increase the number of responses. See, if I click 2, I got an additional row indicating that you can enter another response parameter. Okay, so if you're ready to go with your responses and their units, if you enter them, you can again click next. Then what it will show? It will show you some power of the study. Okay, power is it is indicated as some 57.2 by default. When you change the parameters, when you give correct values, then you will get some other values in the power. So it is better that your power must be 80% or more, so that your design has enough strength to identify the influence of factors on responses. If you click finish, see, all these are in coded terms. Coded means, yesterday we have discussed that levels can be given in codes: +1, 0, -1. +1 represents high level, 0 represents medium level, -1 represents low level. So all these are in coded levels. Okay, so if you have given the inputs in the earlier tabs, then actual values may have been produced. So based on these factors, what you get is runs. Since it is 2 cube factorial design, how many runs did we get? 8 runs. 2 into 2 into 2, that is 8 runs. Observe this. So you have combination of different factors. What amount you have to consider each factor is given in this table. As per this table, you have to perform the experiments in our laboratory, note down the responses, come back to the software, enter the responses in these columns, and then you have to proceed further. Okay, so this is the basics. Okay, what you have to understand. And if you observe, there are some other tabs like file, where as usual, like any Word file or Excel file, you have new design, open design, import, etc. And you have certain display options, design tools, etc., which we will see in detail when we take a case study. Now, I will take one factorial design for explanation purpose. Let's take See, let's take one example. Okay, now I'm going to take a 2 power 4 factorial design. Let's take a 2 power 4 factorial design. See, it is a full factorial design where you observe 2 power 4 means how many runs will you get? You can observe it in the left hand side, that is 16 runs, you get 16 runs. Okay, I'm clicking next. Let me explain first what we are going to do. Okay, now we are going to do an experiment based on filtration. Understand the experiment first. My experiment is I'm going to optimize my filtration process. So what is my problem in the filtration process is, as a part of filtration, I am using one filter aid. Okay, filter aid, what I am using is formaldehyde. So what is the problem in my experiment is, there is a regulatory constraint. That means the concentration of formaldehyde, what I am using in my experiment for easing my filtration process is very, very high. I can't use that much quantity. If I use it, that process will be disapproved by FDA people. Regulatory authorities will disapprove my product. Hence, I have to optimize. That means I have to take as less as possible formaldehyde concentration. And I also want a maximum filtration rate. So my desired response is filtration rate at which filtration is happening. Okay, so these are the two objectives that I am going to optimize. Let's see the design first. See, my experimentation is regarding filtration. I have a problem with the concentration of formaldehyde, which is used as filtration aid. I have to optimize the concentration of formaldehyde. That means I have to take as minimum as possible. And I also want a maximum filtration rate. So what are the variables that are influencing my process are temperature, pressure, concentration, stir rate. If you remember in the yesterday's session, we have discussed about critical quality attributes, right? So these are CQAs. Among all the QTPPs available for filtration, we have selected only these factors as critical quality attributes. Okay, so those are the responses that I have selected. Filtration rate is the response, and the factors which are influencing filtration rate are temperature, pressure, concentration, and stirring rate. So I have 4 factors. I want to analyze them at 2 levels. Hence, what am I using? A 2 power 4 factorial design. Let's go back to the design expert software. Let's see how it works. See, so my 4 factors, I am noting down the factors here. The first factor which we are analyzing is temperature. The units of temperature are degrees centigrade. And the second factor which I am going to analyze is pressure. Look how I'm giving input parameters, okay? Pressure is measured in PSIG units. Third factor which I'm going to analyze is concentration. Concentration is measured in units degrees centigrade. Fourth factor which influences my filtration process is stirring rate. So stirring rate is given in RPM. I will give my low and high values. For temperature, my low value is 24 and my high value is 35. So I must not go below 24, must not go beyond 35. The limits for pressure are low value is 10, high value is 15. Concentration of filter aid, that is formaldehyde. We told in the problem statement itself, I have to use very less quantity of formaldehyde. Optimizing this one is a very, very important parameter for me. So I will take the least permissible amount 2 is the lowest value that I can take. And last one, string, it is the minimum value is 15 RPM and maximum value is 30 RPM. So what I did is I have inserted my factors influencing filtration rate along with their units, and I have fixed their levels. Okay, we'll go to next. Now it comes to response. What is my response? It is filtration rate. Filtration rate is my response, right? So what is the signal to noise ratio? I told you, right? We are going to study the signal to noise ratio also. See, what is meant by signal is some response which is given, which is very significant in identification. That means if I get a filtration rate, let me fix the units of filtration rate also, it is gallons per hour. Okay, so signal to noise ratio and signal and noise ratio, what if I don't give, is also what we have to analyze. Let me proceed with this. Observe this one. What is the power of the study that I have got? 95.3%. I told you priorly that power of the study must be greater than 80%. If it is greater than 80%, the study is good to go. That means the design is strong enough to analyze the influence of factors on responses. But yes, the power is good. But what about my signal and noise? I have used the default information. I didn't exactly give. Understand this. What is signal is, what is the filtration the rate difference that you feel that is significant? Okay, I feel that 10 gallons difference is significant. So if one run to other run, if you find a difference less than 5 gallons per hour, you don't consider it as a response. Okay, so less than 5 difference in result is not significant for me. Then this becomes 10 becomes my signal, 5 becomes my noise, less than 5 becomes my noise. Yes, we will proceed further. Yes, since the signal to noise ratio is 2, even in the before attempt, default value is also 2, and now also it is 2. Hence, we didn't get much difference in the power of the study. Power is good. That means my design has enough power. So what I will do is I will quickly click finish. Observe this one. What did we get? We got 16 runs. Since it's a 2 power 4 factorial design, what we got? We got 16 runs. Now what I have to do is I have to go to the laboratory, use each parameter. That means I have to perform 16 runs. Okay, 16 runs in this ratios. That means run number 1, I have to maintain temperature 24 degrees, pressure 10 psig, concentration 2. Concentration is 2% and stirring rate is 15 RPM. See, we have entered a small mistake. Look, the concentration should be given in percentage. By mistake, we have given it in degree centigrade. What you can do? Edit info. You can go like this. You can change concentration into percentage. You always have this option. Okay. You just have to do a right click. That's all. Yes. So run number 1, what I will do? I will take given parameters. I will execute the filtration process. And what is the filtration rate I have obtained? I will note down here in this table. Okay. I will perform all the runs. And then what I will do is I will note down the values. Imagine that I have performed the runs. And now I am going to enter the values. Okay. So let me enter the values quickly. Yes. So you have to do the experiments. We already did the experiments and we got results. That's why I could enter the values, responses I could enter. Okay, now what is happening is I have my runs, I have my responses. What I must do is, see, I must proceed with the design. Let the software do the magic. Now let's check once. What is the summary of the design? It is a factorial design, which is a two-level factorial design with the two-level factorial design. If you observe it, we have two levels, four factors, right? Four factor, two-level factorial design, 2 power 4 design. Observe the summary of the factors. See, we have four factors, each with their minimum and maximum levels. We have one response, and since we have given response values also, it could take the minimum response and the maximum response from the data and calculate the mean response. So my mean filtration rate is 70.06. Okay. So now I understood the summary of this experiment. I will start moving further. Look, I'm going to analyze the graph columns. Observe this one. So here you can observe what is the influence of temperature on filtration rate. You just watch, have a look at the right. You can see one table here. See, some red cross marked table. Observe this one. This table has some interesting information. See, if I change the block where it is focused, you can observe a change in this graph columns also. So please focus on one area where, other than this diagonal red squares, observe an area where you can find another red square. What is this red squares indicating is this one. That means you take the upper parameter in that row, temperature. What is the lower one? Filtration rate. So temperature is having very high influence on filtration rate. That is what you have to infer from this one. From this is a scatter plot, and this one is a correlation matrix. And if you observe the correlation of each factor that we have taken in the experiment on the response, temperature has very high influence on filtration rate. And also, if you observe, stirring rate also have a little more influence. Concentration also have certain influence. Pressure is the least influencing variable on filtration rate. It's not showing much difference. Okay, so you have to analyze this data like this, graph columns, the interactions and all, you can analyze from this table. So if you move further, we are going to see the left of this window. We are going to evaluate the design. When you are evaluating the design, you observe here, we got a process order. We didn't select this order. The design expert software itself have selected, right? So observe the model type, it is factorial. And you, if you have a doubt regarding the power options, you can go check for power options once, give apply, say okay, then you can proceed further. And you observe here we got some terms which were included in the model. Sometimes we may get some yellow asterisk marks, red marks, blue marks, etc. Observe, if we get some term like represented with the symbol E, you have to understand that that term is not included in the model, because it is having a negligent effect. If you get some term with into mark, again it is also indicating that it is not included in the model, because it is causing some unwanted interactions, unwanted effects. Now, if you move further, we are calculating the results. If you press results, see, the software is calculating the result. And if you observe, there is no power here. And you can also observe a warning sign. Power is not defined when the residual degrees of freedom are 0. The beauty of this software is whenever you click, when you don't understand something, if you click on that, it will automatically direct you to some help menu. Okay. So what is it saying is, consider removing some model terms from the power model by clicking back, edit model, or add more runs to the design. See, what we'll do is, I will go back to the model. I'll go to the design. What I will do is, I understood at that point that my design is not going well. It is not working properly. So what I do is, I'll take the design tools. What I do is, I'm going to give it some support. It is suggesting that you need some more additional runs so that you will better design the experiment, better get the results. So I'm going to augment the design. That means instead of only 16 runs, I'm going to add some more runs. What will be added? It is suggesting, the software itself is suggesting you can go for an augmentation where a central composite design is selected, some center points and some axial points will be added to the design. Do you remember what center points and axial points are? Axial points are out of the box, out of the cube points. Center points are middle of the cube points, right? So those points will be, those runs will be added to the design expert software existing runs. Okay, if we click OK, and there were how many axial points are added, how many center points are added is given in the table. I will click OK. See, some more runs were added. Now you have to again perform these runs, add some values for this table, and then you can proceed further. Okay, see, again, let me take this. Yeah, if you observe, when additional runs were added, what happened to the power of the study? You got a very good power, 99.9%. Now model, the design is strong enough and to proceed further. Observe the graphs now. See, this graph is representing FDS. FDS means fraction design space. What is this graph indicating is, how are you going to interpret this is, you observe a line here, see, and fraction of design space is observed. Till some extent, the graph is a straight line. After that, it's a slight curve, right? Till what extent is this graph a straight line? If you observe, it is still 85% or around 85%, right? Or 0.80%. So what is this graph indicating is, till 80%, till 80%, 85% chances are there for your design to be very inert, very strong enough to perform your experiment. See, after that, there will be slight deviation in there may be chances for error to obtain. So standard error here, it's a curve, it's not following linearity. So above this fraction space, above this percentage, there might be chances for getting error. Till this percentage, you are good to go with the design. Then we will go with constraints. If you have any constraints or conditions that can be added, you can add. As of now, we don't have any conditions. Now I'm going for analysis. Look at the left tab, analysis. So what is my response? Filtration rate. Filtration rate is to be analyzed. I am going to analyze the filtration rate. I will click start analysis. So what the software did, when I click start analysis, it analyzed the data and it is suggesting which model, mathematical model is my experiment belongs to, where it is linear. I mean, which model is it following? So actually we thought that it might be quadratic, but it is aliased. There is a red mark saying that it is aliased. What does it mean? Aliased means if you take this model, you will get some unwanted effects where the result will be confusing. Okay, interaction effects are misinterpreting, misguiding. So this one is skipped. What is suggested design is 2FI design. So we will take its suggestion and we will go further. And you can also observe some values here. P-value, if you remember P-value, you might have studied whenever P-value is less than 0.05, what does it mean? Null hypothesis is accepted. So P-value for this design, non-2FI versus linear design is suggested. So it is always better to take the software suggestion. Now I will move further. So we started analysis. We had this one suggestion by the software. Then we will go with model. Observe, there are some additional terms added. Okay, all these terms which don't have any mark here, which are in green color, will be included in polynomial equation that we obtain. Then I'm going further for ANOVA. See what it gave for ANOVA. The model is significant. We took its suggestion, we proceeded further. Then every time when we do analysis of variance, what we must get is the model must be significant. Observe the R-square values. This is very important area, fit statistics. You have to observe R-square value. You might all have drawn a calibration curve where R-square must be, what is the indication for what is the value R-square must be? It must be nearer to 1 so that linearity exists. So observe the R-square value, it is around 0.977. It is near to 1. That means the model which was selected by the software has linearity, indicating linearity. Now, there are some other parameters which are indicated. See, model F value. Here we didn't get model F value. See, F values are given. All of them are having significant influence. Now, if we go for observe this area, see, coefficients in terms of coded factors, coded equation, actual equation. Let's see this equation. Have you ever observed a polynomial equation? Whenever you go for ANOVA, you will finally get a polynomial equation, right? So the polynomial equation for this experiment is this one. That means if you write it as equation, it will be like 10.81a plus 1.56b plus 4.94c plus 7.31d plus 0.0625ab, etc. All plus signs indicate that when you increase this factor, there will be an increase in the response. Minus signs indicate that when you increase these factors, you will have decrease in the response. So this is where you have to note down the polynomial equation. Then next, going to diagnostics, you have some beautiful plots given here. Observe the first plot, that is normal plot versus residual plot. See, I'll show you in a bigger way. Yeah, see. Observe this one. Whenever you see a plot like this, what you have to observe is there is a mean line given at the center, and the points are scattered at the both sides of the line. So whenever you find points nearer to this line, you don't need to worry. You have to observe some points which are far away from this line. Observe this point. These points are called as outliers. Okay, so they are out of limits. They are causing some non-linearity. If we have any problem further, we must go with this run. If you click on that, it will show which run is it. It is run number 2 with this combination. Then you have to re-perform or adjust this run or think about optimizing this run. If you don't have any problem, you can proceed further. Most of the points are falling within the limits. Hence, we can move further. Observe this plot, the next plot, that is residual versus predicted plot. See, softwares is representing some values. You have a mean line and the points scattered. Again, if you observe, one point is slightly away from the other points, the same run number 2. And if you observe 2 red lines given on the top and bottom, what you have to observe in this graph is no point falls above the red line or below this bottom red line. If points are falling above the red line or below these, beyond these red lines, if some points are existing, what does it mean is there is more error in the data that you are going to get. So always be cautious about that. If you have errors, you have to go back and optimize your design. Also, the next one is residual plot. This one is called as residual plot. You observe the residual plot. It has some pattern. Observe this. So every point, if you select, it is representing one run. All the runs are plotted and they are joined with the line. Again, for this one also, if the points are in and around this center line, mean line, it is desirable. If points are far beyond the line, like this, you must be cautious about the result, okay? If it is out of this red line, beyond these red lines, then it is an alert. Then observe this plot. This is Cook's distance, where you can find another red line here. Always red represents a stop mark, a warning sign. So no point is beyond this Cook's line. Says this distance, beyond this distance, no point is there. Take care that no point is beyond that line. And the next plot is predicted versus actual. This we have covered in the yesterday's presentation also. If you observe these points, look, there is a mean line, and one side there are predicted values, other side there are actual values. If you observe, all the values are very near to the mean line. That means the predicted values and actual values are very much similar. Design expert software could predict. It is also predicting simultaneously. You are doing experiments and it is also predicting what might be the result. So what is the actual value, experimental value that you have given, and what is the predicted value for given by the software? Both are going hand in hand or not, is what this graph is representing. If points are very much scattered, that means it indicates that there is a difference between the actual values and predicted values. Then you have to go back to the experimentation session and again reperform the experiments once to check whether there is any experimental error. Okay, this graph is very important. Then observe this residual graph. Same, most of the graphs have red lines where points must not fall beyond the red lines, and every point, if it is near to the mean line, is suggestible. Then there is a leverage graph. See, there is a mean line and all the points are falling onto the line. Yes. This one, this is another DFITS graph, DFF-ITS graph, and you have two blue lines. You have to observe that this no point, no run is beyond, far beyond this blue lines. See, we have one point which is beyond the blue line. We have few points beyond this here also, 2 points, but these are at least very slightly near to the blue line, but this point is far beyond. Observe this run. What is this run? We have an outlier always, right? But it is not beyond the limits, the run 2. That is what we have to be cautious about. We can do a highlighting. Okay, highlight this point. We can be cautious about that run. So we can do that highlighting point also. Then, so this is what is the summary of the report. Look, so little outliers. See, I told you when we observed this DFF-ITS, 2 points were below the bottom, below the bottom blue line. 1 point is above the bottom upper blue line. That is run number 2, run number 7 and 8. So you must be cautious because these are fair. These runs have fair chances for getting any error in the result. So we will move further. So we have analyzed the result. We have performed analysis of variance. We have observed. As of now, we don't have out of the limit result. We don't have. So we can proceed further. So I'm going for optimization. Observe, we have 2 types of optimization, that is numerical optimization and graphical optimization. When you consider numerical optimization, if you see the screen, you have all the 4 factors and responses. This particular tab is asking for your goal. Okay, so what is your desired temperature? That means what is the goal for your temperature? I want my temperature to be minimum. I want my temperature to be maximum. If I have any such goals, I can give that goal here. I can give a specific value. My temperature must be only equal to this value. Like that I can give. If it is in range, if you select in range, it will be by default take the lower limit and upper limit which we have given for that factor. The next parameter is pressure. Again, it is in range we have given. Third parameter is concentration. What is this concentration? Concentration is concentration of formaldehyde. We have an objective. If you remember, we want our formaldehyde to be minimum, right? So we thought of doing that. We want to optimize the concentration of formaldehyde to be minimum. So what I do is I will click, my goal is formaldehyde to be minimum, and stirring rate, it can be within the range. And what is my objective for filtration rate? I want my filtration rate to be maximum. See, you are giving your goals. What you want to achieve is what you are giving to the software. Then the software will do what the software will do. It will pick solutions. You have a design space, okay? Among the design space, see, I'll show you here. Yeah, sorry. So you gave your goals, you got some solutions. Observe how many solutions you got. Based on your goals, you got only one solution, okay? What is the desired solution that you got? This one. Temperature is 35, pressure is 15, concentration is 2, stirring rate is 30. That is the run suggested by the software. You can go with this run, take this run, again perform that run in your laboratory and check whether software will perform this run and predict the value, that is filtration rate. What might be the filtration rate when you employ an experiment using these conditions? You have to perform the experiment in your lab and analyze whether your experimental value and the software predicted value are same or not. Okay, so you have like this is desirability. You also can do some graphical optimization where you have only contour plot. What is it representing is you have a wide design space where you can take any option. Here, design space is fixed. Now we are going to do post analysis. See, observe this one. I told you, right? So you can pick, just a minute, I'll show you what is the run number here. If you go for numerical optimization, and the criteria, the solutions, ramps, observe there are 100 solutions and you are being shown only one solution out of that. You can see n number of solutions, okay? There are 100 solutions given. So if you want to still minimize the solutions that you get, what you can do is, I want my temperature to be maximum. You can make the stringent decisions while you are fixing goals. You can keep the concentration as minimum. You can keep the stirring rate as maximum. I'm not doing it as fluke because if you remember the first right side, we got a fit statistics graph, correlation graph. If you remember, one factor is having very high influence on filtration rate. We observed that temperature is having very high influence. More is the temperature, better is the filtration rate, is what we have observed in that. So that based on that inferences, I am fixing my goals. So again, I can go for solutions. Now you can see there were only 98 solutions. You can still go for a stringent solution, and among the available solutions, observe the desirability value. Whenever desirability is nearer to 1, it is your most preferred solution, okay? So observe, my second run is having desirability 0.989. My third run is having desirability 0.989. So if I take in this way, I can pick any 3 to 4 runs and then I can go for experimentation purpose. So when I go for point prediction, post analysis, I go for point prediction. Look, I will go for any run. I will take any 4 runs, 1 to 4 runs. What I do is I will perform the experiment and then I will add those values here. Observe, there is an empty column here. It has predicted some value, filtration rate might be this much. You have to do the same experiment in your lab and observed value must be noted down. Then it will calculate, then we can calculate, the software itself also will calculate mean values. That means difference between the predicted value and observed value. Imagine that you have performed the experiment and you got a value of 68.12. Okay, if you enter that value, and ask for a mean value, you will get what is the standard deviation that you get. So if the observed value and the predicted value are very much nearer, then you can say that your experiment is good at analyzing the responses. So that is how you have to do perform the experiment and analyze the data. So we will go back to the PowerPoint where we have started with the objectives. If you remember, what is the conclusion from this after performing design experiment? What did I get as a conclusion is, I got a run which can be taken as such so that my filtration rate is maximum and formaldehyde content is minimum. Okay, so that is what is very much important, because that is my objective. So in the same way, we will see another example also. What we have seen earlier is a full factorial design, which because of the power constraints, we have augmented it and went for another design. Now we will see a response surface methodology, that is Box-Benham design. Observe this one. I will open Box-Benham design. Yes. See this design once. So what is this design is? What is the objective of the design is? We have a problem. That means what I want to achieve from this experiment is, this one is, my objective is to prepare some mucoadhesive microcapsules. It is a terminology which you understand. I want to prepare some microcapsules which are having sustained release. So my objective is sustained release. That means minimal drug release. And these are mucoadhesive microcapsules. Hence, I want a very good mucoadhesive strength also. So those two are my objectives behind the experiment. So what are the factors which are altering these two parameters are the mucoadhesives that I have considered. I have 3 mucoadhesives in the formulation. What is the concentration of each mucoadhesive that I have considered are my factors which are varying the responses. Then what is my response? I'm calculating the drug release at 12 hours since it's a sustained release microcapsules. And I'm also calculating a parameter called mucoadhesive bond strength. Then we will see how the design is. Yes, observe this one. So what we are going to study is a response surface method. What is the design that we have considered? It is Box-Benham design. And the input parameters that I have given factors are gum A, gum B, and pectin. For confidential purposes, we didn't name the gums. You can imagine any gums that you like let's say it's tragacanth, gorgum, pectin, etc. So we have 3 gums at different concentrations. I've given a range. That means my minimum value of each gum is 0.5 and the maximum values are ranging from 1.5 to 3. So now what I want to achieve, what are my responses, desired responses? DL is drug loading. DR is drug release. So what I want is, I want maximum of the drug to be loaded. I want a sustained drug release. Then if you observe the design. When you select Box-Benham design, I already know that what are my factors, what are my responses. I gave the design straight away. I have selected Box-Benham design. I got several runs. I have performed the experiment and I have entered the response values. Observe this one. So my graph columns are like this. You observe this one, the right side, the correlation matrix. Did you find any highest influencing factors here like the previous example? No. Yes, you have certain factors. See, observe, accept the diagonal ones. If you find any red lines, then you have to be cautious about those factors. Yes, you have number 1 and number 2, two red squares. Observe them. So what are they indicating is this one is the influence of pectin on drug loading. Pectin concentration is having highest influence on drug loading. Also, if you take this box also, it is indicating the same. Drug loading is very highly influenced by pectin concentration. So you observe. So by this table itself, we understood what is the factor that is having very high influence on the response parameters. What do you mean by drug loading here? Amount of drug that is incorporated into the microcapsules. Okay. Then if you move further, if you evaluate the design and if you calculate the results, you will get the power of the study. Observe the power of the study. See, A square, B square values have 90% power. ABCs have 68% and ABAC interaction effects have only 40% power. Now my question is, we have discussed that we need 80% above power so that my design is strong. But I got some powers like 68, 40 for some parameters. Can I proceed further or not? The answer is yes. Until and unless you have some outliers, you can go for the experiment. You can proceed further and check if you have any outliers. If you have outliers, then you must go for augmentation or further increase in runs, etc. Observe the graphs. What is this? Fraction design space. So observe this, what percent till what percent is it linear? It is only up to 80%. Above that, there is a non-linearity. So this that means this design is perfect in analyzing the influence of factors on the responses in this percent. Then if you go for analysis part, that is drug loading, and if you analyze and observe the results obtained, if you see the fit summary, what model is it selected? Earlier we had it as 2F5, but now what is the model that it has selected? Quadratic, right? So the quadratic is having p-value less than 0.05, hence that model is selected. Then if you move further, fit summary, then if you go for the model terms, then if you go for ANOVA, see, observe this one, you have another 2 rows added additional to the earlier example. See, the model is significant, you have got a lack of fit. See, whenever you go for response surface methodology, what is the advantage is you are going to analyze the curvature effect also. Yesterday we have discussed about curvature effect, if you remember. So curvature effect is also analyzed with response surface methodologies. Hence you get this additional parameters, that is lack of fit. Lack of fit is not significant. It says that there is no much significant curvature effect. So you can proceed further. Otherwise, if lack of fit is significant, what you have to do? You have to add some center points also, some additional points also, so that lack of fit becomes lack of fit is not significant. Linearity exists. Then observe the fit statistics R square value. Is it nearer to 1? Yes, it is nearer to 1. It is 0.98. Then observe the polynomial equation. Observe this. Yes, you have AB, AC, BC, A square, B square parameters in the polynomial equation. Most of them are having positive sign. Only AB interaction is having negative sign. Then if you move further for diagnostics, observe the graphs that are present. What is this? Half normal plot. Observe any outliers are there. See, in the earlier example, we had one point which is far beyond this line here, right? A green dot. But in this one, you are not observing any such outliers. Okay, so it is good. That means all the values are very much nearer to the mean values. Next graphs also, did you find any outliers? No, we didn't find anything. Even at the residual plot also, you didn't find any much deviation. That means no points beyond the red lines. Box-Cox plot, observe this. Yes, it is okay. Predicted versus actual, you don't observe any points which are very much distant from this mean line. Hence, the predicted values and actual values are very much nearer. Then, if you observe this DFFITS, there are some points which are beyond this blue lines, but not very far beyond. Finally, you have certain slight deviations observed beyond the blue line, right? So those are these highlighted points, blue highlighted points, which have slightly exceeded the limits, but that exceeding, that means that amount exceeded is within, not beyond the acceptable range, hence we will proceed further. In the same way, you can also analyze the graphs. The beauty of response surface methodology is you get some beautiful 3D response surface plots. Observe this one. This one you don't get in the previous example. See, if I take pectin on X2 axis, observe this 3D response surface plot. See, you can rotate this graph like this and observe this one. What is the influence of gum A on drug loading? If you observe, it is a flat line. That means there is no much influence of gum A on drug loading. Let me rotate this graph to pectin axis. See, if you observe, what is the influence of pectin on drug loading? When the concentration of pectin is increasing from 0.5 to 3, the drug loading is also increasing. Observe this one. There is an upper moment of the 3D response surface plot. This is how you have to analyze the 3D response surface plot. You can change this axis. That means I have A and C on my X1 and X2 axis. You can use A and B. You can use B and C like that. You can change the parameters what you want on X1 and X2, and you can analyze what is the influence of that parameter on the response. Yes, you have contour plots also. This is a 2D way of representing the same what we have seen in the 3D response surface plot. Then if you observe the same process you will do for the second response parameter also, same fit summary. And observe this one. You got a quadratic model selected for drug release. Does it mean that you will get the same model for you got quadratic for drug loading? Does it mean that you get same response for drug release? Means no. This is another response. The values differ, the parameters differ, and you got another mathematical model suggestion from the design expert software. Okay. So here the suggested model is linear. Remaining all parameters are same. Check for the ANOVA table whether the model is significant or not. Lack of fit is non-significant, so you don't find significant curvature effect. You can check for R-square value, any outliers present, model graphs. See, you observe this one. There is one plot called interaction plot. This one is important. See, if you observe these lines are parallel to each other like this, then you can conclude that there is no much significant interaction. If you observe some crossed lines here, then you can identify that there is some interaction present between the factors which were considered. Then you can also analyze that interaction effect. What is the interaction effect? You will get that data from the polynomial equation. The 3D response surface plot, again, we will just change this parameter and check how the 3D response surface plot is. Observe the influence of pectin. When I have increased the concentration of pectin from 0.5 to 3, what happens? What happened to my drug release? It decreased. In the earlier case, drug loading is increased when the concentration of pectin is increased. But here, drug release is decreased when the concentration of pectin is increased. Is this my desired response or not? I want a sustained release mucoadhesive beads. So this is what is my desired response. Yes, we will go for optimization. Yes, as mentioned earlier, we will fix our goals. What do we want? What is my goal for drug loading? I want maximum drug to be loaded in my microcapsules. What is the goal for my drug release? I want minimum drug release. Then I will click for solutions. There are 80 solutions given. You can click, you can check for the desirability values and take any 2 to 4 solutions. You can go for experimentation again. Then you can enter the values in the prediction table. You can do a confirmation test. Same as mentioned before. So this is how you have to use design expert software. So we will see what we have studied now. So what we did is my objective for the experiment should be very clear. I want sustained release mucoadhesive beads. I want minimum drug release and maximum drug loading. Sorry, not this is not mucoadhesion, maximum drug loading. So what are my factors? I have 3 gums, gum A, gum B, and third one is pectin. So my responses are drug release and drug loading. I have used a box Banhan design for analyzing the influence of factors on responses. So I hope you have understood how we have did this experimental design. Now we will see whether we have achieved the objectives of this workshop or not. See, observe this. We have today in today's workshop, what we did is we have introduced the design expert software, how the software looks like when you open. Today, for this workshop purpose, we have used a trial version, the advanced version of design expert software, that is 13. You can also use this software. That means you can take a free trial from statis.com website, but it will be only for 14 days. The free trial is applicable only for 14 days. But what I suggest is in academics, if you want to do experimentation, this will get, that means you will get expertise only when you practice. Okay. So since in 14 days, you can't practice much. So what I suggest is you can take earlier versions. That means design expert version 7, 8 are freely available for download. You all can download that earlier versions. There will be slight difference with what slight differences with what we have seen today and what is present in 7 and 8 versions. But it is very much friendly with you. That means it will not be very complex. You can easily use that. Start using, start exploring, do some experimental trials, put some input, give some responses. You can try. Whenever you practice, then only you will get to know, you will understand how this software will help you design your experiments. Then we have seen the design wizard, new design. Sorry, I have not shown you the design wizard. Just a minute. Okay, see, when you open design expert, you will see like this, new design, open design, import data and design wizard. If you go for design wizard, if you don't know what design to select, for beginners, it would be always better to go for design wizard. So it will ask you, the software will all through the process will guide you. It will ask you, what are you going to do? What is your purpose of you designing your experiment? Are you going to screen? Are you going to characterize? are you going to optimize? Screening, when do? We have, if we have more than 6 factors, if you want to know what are the most potential factors, then you will go for screening. Characterization, when you will do, when you have more than 10 factors and you want only less number of runs, then you will go for characterization. Optimization is what you do when you have limited number of factors, less than 6 factors, and you want to know what is the design space for that factors, then you will go for optimization. After doing optimization, you will get a control space. Okay, let's say I want to go for optimization, then it will again ask you, what is the type of design that you want to? If you click on that, it will give you some information, whether this design is suitable for you or not. You can justify yourself using the matter given beside it. It will give an example also, very user-friendly software. When you will go for a mixture design is, if you are having factors which are part of a mixture, then you will go for mixture design. If you are having some numeric factors or categoric factors, then you will go for factorial design or response surface methodology. This is the most commonly used design among all the designs. Then if you have both the mixture design, mixture type of factors and the numerical and categoric factors, then you will go for combined design. Let's say if you go for combined design, it will ask, do you have any hard to change factors? That means I can't vary beyond this. My temperature must be this much only. I can perform only at this temperature. If you have such factors, I can't change, then you can click S. If you don't have such factors, you can click no and give a finish. Then it will ask you how many mixture components you have. Let's say you have 2 mixture components. In mixture 1, you have 2 components. In mixture 2, you have 2 components. You have 3 numeric factors, 2 categoric factors. Then if you are giving, as per your requirement, you will give and click next. Okay, you will enter the names of your mixtures, you will give their limits, and again if you give next, see, you observe this, software itself have proposed you a design. Optimal combined design is what is its suggestion. So when you go for design wizard, software itself will guide you which design you have to select, which is better for your factors or responses what you are going to analyze. Okay, so yes, so when you come to objectives, we have introduced what is a new design, how you have to take a new design. We have seen how design wizard will be. Then we have selected how we have to select a design. We have seen how we will build the selected design, how we will give inputs, that means factors and responses, how you will evaluate the design given, that means what is the power of the design. If power is insufficient, what you have to do, what is delta versus sigma value, what is lack of it, what is fraction design space, or how you are going to interpret all these, what are the values that you give, what is the result that you get, what if it is not under limits, what you have to do, what we have seen in the case studies. Then if your power is not sufficient, if you have a lot of lack of it, then you will go for design augmentation. We have performed that in the first case study. Next, we also had seen how to analyze the response if any transformation is required. ANOVA, analysis of variance. We have seen fit statistics. We also have seen diagnostic graphs, model graphs. We have reviewed how numerical optimization is done, how to set a goal, how to give limits, how to draw solutions from it, how to analyze the graphs that are obtained, optimized solution graphs, then how you have to interpret the 3D response surface plots, how you can identify the design space, what you must do after analyzing all this. That means you will get an optimum solution. You will go for an experimentation and you will check whether the predicted value and experimental value are having minimal deviation or not. Then you will go for confirmation. That is what we have seen today. So we have taken these case studies and we have successfully used design expert software for designing those experiments. Not only these, as mentioned earlier, You can use design expert software not only for product development, process optimization. There are many areas where you can use any experiment. You can start doing with simple factorial design. Then you can later on proceed with complex designs. What are present, you can explore. You will get expertise only when you use it. So no field is an exception for usage of design expert. Pharmacology, pharmacognosy, biotechnology, engineering, mechanical, automobile engineering, every person can use this designing of experiments using softwares. Not only design expert software, there are several other softwares also like Minitab, Systat, Statistica, GenStat also. Yes, you can explore any software which is feasible for you and design your experiments in a planned manner. Any questions? I would be happy to answer.
Dear participants, any questions, please raise your hands or mention chat box. Dear participants, any questions, please raise your hand or enter the chat box.
So if you don't have any questions to be asked in this session itself, yes, you can drop a mail for the mail ID is given. We are happy to answer you and guide you whatever be the doubt you have in this explained concept. Yes, I have a question in the chat box. What is filtration aid? See, if you're going for a filtration process, if your filtration is not going smoothly, that means if you have a lot of obstructions, you will use certain additional agents which help the process of filtration go smoothly. Those are called as filtration aids. That means some ingredient which is added to the filtration mixture so that filtration happens easily. Formaldehyde is one example for such filtration aid. It will ease your filtration. But the problem is you should not go beyond the limit. You should not use any ingredient beyond the limits. Every ingredient has their own limits. This quantity is only to be used as per regulatory guidelines. So if you don't have any further questions, what is ANOVA? Okay, another question. ANOVA means analysis of variance. Yes, ANOVA can be used in clinical trials also. ANOVA can be used. See, it is statistics. Whatever data you have, you can apply statistics for meaningful conclusions, to draw meaningful conclusions out of your data. Clinical trials is a very good area where you can apply ANOVA. Yes. If no further queries, I would request Vishwanath sir to please take over the session and talk a few words and give some concluding remarks for the session. In the meanwhile, there is another question. I will answer that. Yeah.
When someone has the question, how to load the drug?
How to load the drug in surface graph? No, you can't load the drug in surface graph. See, whoever asked the question, do you know what is meant by a microcapsule? Or let's leave microcapsule. You know what is meant by a dosage form, right? Sir, let's take a capsule or a tablet, etc. You think that whatever quantity you add, means a tablet or any formulation will have multiple ingredients, right? Drug and excipients. If you think that all the drug that is added into the formulation comes into your dosage form. I mean, my dose is 500 mg, my drug dose is, I think that every tablet I have manufactured will have 500 mg drug. So what is the actual quantity of drug that is present in each tablet? You call it in synonymously as content uniformity. Okay, so in tablets, the term is content uniformity. In microcapsules, what is the amount of drug that is incorporated into the microcapsules? You designate it with the term called drug loading. Drug that is incorporated into the microcapsules. Okay, that is one parameter. How much amount of drug got incorporated into the formulation. So my primary concern is my drug should not go waste. Most of the drug must go into my formulation. Okay, usually microcapsules are done with various methods where you use stirring. So a lot of drug gets adhered to the walls of the beakers or walls of the vessels that you use. Excipients and drugs go waste. So there are fair chances for drug loss or fair chances for less amount of drug being incorporated into the microcapsules. And that's why I took that parameter as a critical parameter, critical attribute. So drug loading is important.